So in the last lecture, I want to talk a little bit about the propagation of smallness for the gradient that I mentioned in one of the previous lectures. I'll try to formulate the statement and tell you how to prove it. So and this part is based on our joint work with Sasha Logunov, and really I will explain you that the basic argument is Logunov's induction on scale that he used to estimate the size of the zero set. So we're in this situation where A is a symmetric elliptic matrix, but as always, we will think about the Laplace equation without using very analytic tools. And we want to get an estimate for the gradient in the following way. We want to know that the maximum of the gradient over half ball is bounded by constant maximum of the gradient. Let me write epsilon to the power alpha times the maximum. Where epsilon is the maximum of the gradient on some set E, and everything is normalized so that the maximum of the gradient on the union ball is equal to 1. I want to write it in this way to say the following first. We expect that if set E is thick enough, so the codimension is less than 2, then there should be some uniqueness theorem. If the gradient is vanishing on this set, the function is 0. If there is uniqueness theorem, there should be some quantitative way to make this theorem hold for some function. So we believe that if we have estimate like that on a set of codimension larger than 1, so for the moment the set is fixed, then there is some function of epsilon that goes to 0 when epsilon goes to 0, which this estimate holds. It just basic compactness ideas and uniqueness theorem. And we want to understand for which sets the estimate is like that, and it would be nice to know that as soon as you say control the Hausdorff content of this set of order larger than n-2, you have this estimate, but we are not there. And the result that we have is that if Hausdorff content of E of order n-1 minus delta is given, then there are C and alpha such that the estimate holds. And I'll try to explain you where this bound for the Hausdorff content comes from and how this is proved. This is version of the Remus inequality in a sense, but instead of the measure, we use a different way of measuring the size of the set, and we're doing it for the gradients. And it's easy to see that this is equivalent to the following statement. Let E A be set at the half ball where the gradient is bounded by e to minus a. Remember, we normalize the gradient so that the maximum of the whole ball is equal to 1. And our statement is equivalent to the fact that the Hausdorff content of this set is smaller than or equal to constant e to minus another constant that I note by beta a over n, where n is the upper frequency of our function in the unit ball. So the initial result looks like it has nothing to do with the frequency, but as soon as you have the ratio of the maxims of the gradients, you can relate it to the frequency function, and this is a reformulation in terms of the frequency function. So we want to prove this result, and we're going to do it using induction on n, more or less. Let me say first what we know. This inequality is trivial when a over n is not very large, small. Let me think. If a over n is less than a constant, then the estimate is trivial. Remember, by using Hausdorff content of a set, for any set, the Hausdorff content in the unit ball, the Hausdorff content is bounded by 1. And if this is small, I can choose a constant here to make this larger than 1. So this is trivial. But I need another base of induction, and it's where the work of Naber and Valtorta, Chigir, Naber and Valtorta is useful, is that I also want to claim that if n is bounded, then this holds. For this one, this holds for any beta and c that depends on beta c0. And for that one, we will say that it holds for beta small enough. So my induction base, I want to understand what happens if the frequency is bounded. And to argue about this case, I don't care how bad the quantitative estimates of Naber and Valtorta are, if it's double exponential or anything else. I just need some control of what happens when the frequency is bounded. And there is the following way to reformulate the result. Starting from now, I will prefer to work with cubes, not balls, because it's easier to divide cubes into cubes. Suppose that I have a cube and I divide it into many by fixed number of smaller cubes. So Q is union of small cubes, the number of cubes is b to the power d, d is our dimension. And we say that a cube is bad if the infimum of the gradient over this cube is less than a small constant times the supremum of the gradient. Like that. So in particular, if there is a critical point, then the cube is bad. But with choosing this constant small enough, you can see that these bad cubes are covered by our effective critical set. Where the scale, the parameter, should be proportional to the side of the small cube. So let me assume that this Q original one was the unit cube. Then there is a constant over b to the power. And we know that this is not large enough. We know that we can cover it by some of the cubes. We don't need all cubes. There are some good cubes. So what I need from the argument of Nabernois-Torter is that when b is large enough and zero fixed, there are some good cubes. Moreover, the number of bad cubes is bounded by a constant b. Yeah, I decided that my dimension is d, so I should try to write it like that. What we're trying to say is that this set, if we fixed and zero, and we try to look at the set where the gradient is small, smaller than some constant, we're able to cover it by balls and estimate the Hausdorff content, and then just repeat this procedure, cover each ball where the gradient is small by new ones, and you will get exactly estimate of this kind. So here n is fixed, a is what we change. We do one step and show that the Hausdorff content will be less than 1 of this order, and then we repeat it inductively and get that it goes to 0 as exponential a here. So this some estimate of the effective critical set of neighborhood order gives us base of induction and tells us that for fixed n, we know that we can choose beta small enough so that this holds. And the rest is very general. There is no much hard analysis there, but there is a very nice lemma that I said, as I mentioned, this combination of simplex lemma, hyperplane lemma, and some iteration, and goes like that. Let me finally define what is a frequency function in a cube. I want to take supremum over x in cube and r, that is a constant times the diameter of this cube of the upper frequencies here. Where inside the domain, everything is monotone, almost monotone, so there is no chance of this thing blowing up. We control the frequency on large scale, we control it in a smaller one. Be a little bit more careful because it's upper frequency, but still there is no chance this will blow up. And then in terms of this frequency, there is a nice combinatorial lemma of Sasha-Logunov that if the frequency in a cube is large enough and Q is written as a union of equal cubes of smaller size, 1 over b of the original side lengths, then the number of Q such that the frequency on a small cube is larger than n over 2 is bounded by b2 minus 2, d minus 1 minus the constant. So there is a large b and a small constant delta such that this holds as soon as the frequency is large enough. By the definition of the frequency and monotonicity, it's easy to, even without monotonicity, it's easy to see that for each smaller cube, the frequency is smaller than or equal than for the large cube. This n is the frequency of the large cube. And we're saying that in most places, it is smaller. Places where it's like that. This is. And using this lemma, we are going to do induction and prove the estimate of the Hausdorff content of the set where the gradient is small. This delta is not the same delta as here, so I should probably, let me write small c here. We'll have to take the delta there to be smaller than this one. And this induction argument is, well, it's important that our codimension is just a bit smaller than 1, and we can go to the codimension 2. So probably a better understanding of the distribution of the doubling of this frequency function will give you the result for the right codimension. So what do? We take the cube and we divide it into small ones. It's what induction is about. And I want to look at my set E as a union of E A intersect with Q. Let us think what happens here. So we write our set as a union of this one. The Hausdorff content is a additive, subadditive function. So you can estimate the Hausdorff content of this one by sum here. But what can I say about this set EA in a small cube? EA is a set of points in a cube where the gradient is smaller than there's a maximum over 2 cube of the gradient. When I go to a small cube and I want to use my induction, the maximum is smaller. But fortunately, we have a frequency function that tells us that this maximum is not too much smaller. So the maximum of 2q gradient u is larger than or equal to a constant to the power minus frequency maximum. Yeah, let me be more careful. So what is this constant? The change of the scale, I had scale 1. This is 1 over b, so it will be like b to minus constant n maximum gradient u over 2q. So suppose that I have an estimate where is it was here. Suppose that I want to prove estimate like that. And I already know it on some, for some parameters a and n, the two base of induction when this is true, or when n is less than c, 0n. I want a recursive inequality for this one using this idea. We take cube divided into small ones, look at cubes where the frequency is less than n over 2 and when it's larger than n over 2. So what happens there? First of all, we're rescaling things, right? So we have a factor 1 over b, and since we're talking about the Hausdorff content of this power, we have to multiply it by this factor, minus 1 minus n plus 1 plus delta. Then when the frequency is large, the best thing I can do is to estimate my function by the same n. But what about a? I have to take a smaller a here. The maximum is like this. So a minus constant n, where c1 is c log b. So my gradient is not as small compared to the maximum as it was, because the maximum is smaller now. But fortunately, I don't have too many of those terms. And then I have a sum where n of q is less than over 2. Once again, this normalizing factor. This is still the case, but here I can put n over 2. Let me try to draw a picture. If this is n, this is a, and I want to have an estimate somewhere here, an. What I know is that when a is small enough, there is an estimate here, and when n is small, there is an estimate here. What I'm trying to do using this induction is take a point here, move it by decreasing a, and also decreasing k and going half of the scale. It's clear that after finitely many steps, I will be in the region where I know the estimates already. So our estimate the number of the bed cubes here. Remember, it's bounded by b to n minus 1 minus c. It's multiplied by this power, and what we get is delta minus c. And here the number of cubes is b to the power n, and I try to say that my dimension is d, and I always mix it up. But here we'll have e to the power d, it will disappear anyway, so b1 plus delta m a minus c1 n over 2. And what we're trying to say is that if you choose this function to be of this form, this constant plays no role in the induction already, it will disappear. But if this function like that, we can choose beta small enough, depending on this capital B and our parameters, so that this inequality will be true. For the first term, this is larger, but delta is smaller than c, so large B helps you to make this term small. Here, this n over 2 gives you a larger exponent. Here with minus smaller term, and it helps you to beat this as well. So it's a simple algebra afterwards to show that with this estimate, the things converge. this was the proof of this propagation of smallness result. I can give you some other comments, but any questions about the proof? I mean, you can do the algebra by yourself, but the idea is just this: there are many cubes where the frequency is smaller, and on the few where it's close to the maximum, and it allows you to estimate the things. This induction of scales was used by Loganov to prove the estimate from above for the Gauss conjecture, but let me formulate it in terms of the solutions of elliptic PDEs and the frequency function. Exactly the same argument will give you that the Hausdorff measure of the zero set is bounded by a constant times some power of the frequency. Let me write this one. Where A is probably a large constant depending on the dimension. For really harmonic functions, what we know is that you can take the constant power to be 1 here. And it's not clear what is the right, let me write differently. What is the right power in general for solutions of elliptic PDEs. And the second comment, as I said, we want to have propagation of smallness for the gradients. When, say, you fix the Hausdorff content of order n minus 2 plus epsilon of E, epsilon plus alpha, and the maximum of the gradient over E is epsilon. How to do propagation of smallness from sets of codimension a bit larger than 2. And the base of induction is great, but the induction step doesn't allow you to go all the way up there.